All right, so today I had the inspiration because I was reflecting upon the online AP exams this year. Um, and my guess would be, aside from having there be a variety of questions issued to students, but also for any certain type of question, perhaps having variations on what was asked to complete that problem, or just having questions with a variety of ways of solving it. So for example, perhaps we had kind of a simple situation in which we have a block on some sort of surface that has friction, and we need to determine the coefficient of friction between that block and that surface, so to speak. So we need to find the coefficient of friction, all right? So I do recommend you to take a pause here and, well, actually, don't pause yet. Let's say what's given in the problem. So perhaps what we know, or perhaps what we can measure in whatever experiment we're dealing with. Let's see. So first we think mass, but I'm going to make the argument we don't need to use mass. So let's suppose we can measure, maybe if this was moving leftward, perhaps we can measure distance, so we'll call that x. Perhaps we can measure the initial velocity, we can measure the final velocity. It'd be convenient if it came to rest, but nonetheless. Final velocity, maybe we can also measure the time it takes to go from the initial to this final spot. Yeah, let's do that. And perhaps we want to find mu. All right, so take a couple moments here and brainstorm the different ways you think that you can determine mu from these quantities, right? So when I say take a couple moments, take a couple minutes, right? Think through this. Perhaps practice describing in words how you would solve these, since that's probably how these questions will be leaning for this AP exam. All right, so maybe the first idea you had was to use forces, namely with kinematics. All right, I say that, and yet every other idea here will be using ideas of forces in kinematics. All right, but nonetheless, this would be interesting because if we drew, well, I guess I'll draw a free body diagram to the side here because it'll actually be useful for every single method that we analyze this problem. We have our dot representing the center of mass of our system. So that's going to be our mass, our object here, so this block. We've got force of gravity acting downward. We've got normal force acting upward. Those are equal magnitude, opposite in direction, though they are not a Newton's second law pair, right? Because they're acting on the same object. That's not how Newton's second law pair work. But that's not what this topic is. All right, and then we've got friction. Since we've got one-dimensional motion, the force of kinetic friction here is opposing the motion. All right, so looking at our free body diagram, our net force is rightward, which is what we expect since our object's moving leftward and slowing down. Well, I guess I didn't mention that, but since we're trying to find the coefficient of friction here, it's going to be slowing the object down because we have a rightward acceleration, leftward velocity. Those vectors are pointing in opposite directions, so our velocity will, our speed will decrease. So if we're using forces in kinematics, right, we might think, all right, let's sum our forces in our horizontal direction, and that'll equal mass times acceleration, right? Horizontally, we are accelerating. And our net force here, well, there's only one force acting horizontally. That's the force of friction. So we have the force of friction is equal to mass times acceleration. Well, force of friction here, well, we're dealing with kinetic friction, so that's mu times our normal force. And looking at our free body diagram, our normal force is equal to mg, the weight of our block. And that's mass times acceleration. So we can determine the coefficient of friction. Oh, look at this. Mass cancels out. How convenient, because that's an unknown in our problem. We can determine the coefficient of friction if we knew the acceleration due to gravity and the acceleration. Well, we need to figure out the acceleration, and we can use kinematics to do so. So since our acceleration is constant, our acceleration will then be equal to our change in velocity over time. So that would be our final velocity minus our initial velocity divided by time. Again, that's just kinematics. So in the end, our mu will be equal to VF minus, oh, I used VI instead of V naught, sorry about that, divided by time, all that divided by G. I don't know why I put parentheses there, it doesn't matter. But nonetheless, here we have enough information to determine the coefficient of friction using forces in kinematics. A different approach we could take, let me scroll here a little bit. Perhaps we want, maybe what comes to mind is using energy. Right? Another valid way of solving this. Let me actually, well, I guess we'll talk here. Using energy, we're going to be using the work energy theorem. Maybe I'll just start with the theorem. The work done on our system is equal to the change in energy. All right, so of course we need to define our system. Here, well, the simplest system we can have is just the block. All right, so all other forces being external. And here that is an easy system to choose and to use in this problem. So in our free body diagram, all those forces there are external because that dot now is the system that we're representing. Normal and gravity do not do any work on our system because they're perpendicular to the motion, so they do not change the energy of our system, where the force of friction is our external force that is changing energy. All right, so here the work is only the work done by the force of friction is equal to change in energy of our system. And again here, since our system is just the block, there are there's no potential energy. If you just have one object in your system, you can't consider potential energy. You have to have other objects in which you can deal with internal forces. We don't have that here. So when we're dealing with our change in energy, it's just change in kinetic energy. So work done by the force of friction, well, work we know is our kind of quick algebraic formula, FD cosine theta. We can just think here, well, they're anti-parallel to each other. The displacement and our force. Displacement's leftward, force is rightward. So our cosine theta gives us a -1. But basically you can think, well, the work done by friction takes away energy from our system, so it's negative. The force is friction, kinetic friction, mu times our normal force. All times the displacement, and there we go. So there's the work done by friction is equal to change in kinetic energy. So it's 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. And again, mass cancels out. Woo! All right. So from this we can see, without even kind of simplifying it further, since we're solving for coefficient of friction, all we need to know is the acceleration due to gravity, how far the object slides, and its final and initial velocity. All right, so that would give us enough information to solve. Another method that comes to mind is using momentum. All right, so namely here, another favorite equation, impulse momentum theorem. All right, so that's impulse, or change in momentum, is equal to force delta t, namely external force delta t. Now, looking back at our diagram, let's again define our system to just be the block. So all these three forces, normal, gravity, and friction, are all external to our system. Looking at our object and momentum changes, right? Normal and gravity, they both change the momentum the same amount. That's why our object, which is just moving horizontally, doesn't have any momentum change vertically, right? It's not all of a sudden moving vertically at all. It's staying moving horizontally, right? So normal and gravity basically they're not changing the momentum of our system. Friction is, because friction is horizontal here, so it's going to change the horizontal momentum. All right, so it's kind of silly. We're looking at this problem thinking of it as a two-dimensional situation, even though it's just one-dimensional motion, but that might have been just kind of an overcomplicated, over-thorough way of explaining what's going on here. But nonetheless, our change in momentum then is caused by the force of friction. And that makes sense because if this block was sliding and there was no friction, right, it would just keep moving with the same velocity and momentum would not change. So the normal gravitational force you can see here don't affect the change in momentum. But nonetheless, applying our impulse momentum theorem, right, our change in momentum, right, so since our system is just the block, that's mass times the final velocity minus mass times the initial velocity, is equal to our force, that is changing the momentum, that's our friction force, so again, mu mg, times the time that force is applied, right? So here the time that it's applied is the time that it takes for our velocity to go from its initial to final, right? That's that time segment. So we'll just multiply by t. All right, so again, mass cancels out. And looking at our equation here, again, we could rearrange and stuff if we wanted to, but we can look here and see that we can solve for the coefficient of friction if we know the time, the initial final velocity, and the acceleration due to gravity. All right. Now, those are the three kind of general methods that come to mind to solve this problem. All right. Will the AP exam problem be this simple? Probably not. What will be kind of a simple way to make this problem more complicated is rather than having our surface be flat, let's have our block sliding down an incline. Where again, we know that, but let's assume we know all the same values as before, but now we know the angle of the incline, right? Or maybe we know a couple other things, but this would be an interesting way to see what consequences we have, because now, so our normal force is pointing perpendicular to our surface, as a normal force always does. Gravity points straight towards the center of the earth, so here straight down. And then force of friction, so if our block is sliding down the ramp, then force of friction is going to be pointing up the ramp, parallel to the surface. All right, so there's a force diagram. Again, this is not a free body diagram because I'm not representing my block as a free body, but I don't know why I keep saying again. I don't repeat things. I need to break that habit. Anyway, this is interesting because now if we're looking at the motion along parallel to the ramp, normal force is not going to be affecting that motion because it's perpendicular. Friction will because it's parallel to the surface, but force of gravity is neither solely in the perpendicular parallel direction to the surface, to the motion of our object. We have a component of gravity that is pointing perpendicular to our surface and a component of gravity that's pointing along our surface, where this angle here is our angle theta. All right, so it'd be interesting to kind of see and think about how you could apply these different methods of solving the problem to that kind of more complex situation. So I'm not going to go through the details of that here. I think it's a great exercise for you to think about, but it does make this problem more complex. All right, and I would think that would be something more along the lines of what the AP exam might ask you. All right, so I hope that was kind of helpful in thinking about kind of a simple situation and a whole bunch of different ways you could solve that problem. Again, what you might be given on the AP exam, though, may not have all these things given. So maybe you're only given time and not given displacement, right? So then you're going to be forced to then kind of think about things in terms of either forces solely or maybe momentum. You can't use energy in that situation. All right, so just think about what quantities you need to determine certain things. All right. Have a good one.